Welcome to Scoli Sleep Stories. Before we begin, take a moment to get comfortable. Let the day soften around you, and settle in for a calm documentary made for curious minds. If these stories help you rest, learn, or simply enjoy a quieter part of the day, please consider liking this episode and subscribing to the channel. Now, when you are ready, let us begin. Chapter 1. Before Zero. Counting what was there. Long before numbers were written in neat rows, before ink dried on parchment, or signs were pressed into clay, people counted with what they had close at hand. A smooth stone in the palm, a finger lifted quietly, a notch cut into wood, a small token set aside. In the dim light of an early morning, a shepherd might stand near the opening of a pen and feel the soft movement of animals passing by. One sheep, one stone, another sheep, another stone. The flock moved slowly into the open air, leaving hoofprints in the soft earth. The stones gathered in a pouch or a small pile, each one standing for something real, warm, and woolly. Counting began most likely in such ordinary moments, not as a puzzle and not as a grand idea, but as a useful habit. How many animals are here? How many baskets of grain have been stored? How many tools belong to the group? How many days have passed since the moon was full? How many people will share the meal? How many jars were traded, and how many are still owed? The earliest counting was close to the body and close to the earth. Fingers were always available. A person could hold up one finger, then two, then three, making a small pattern of quantity in the air. Pebbles could be gathered from a stream bed and moved from one place to another. Knots could be tied in cords. Marks could be scratched on bone, wood, or stone. A line for one thing, another line for another thing. One more mark, one more stone, one more sheep. Some very old objects have been found with notches cut into them. They may have been used for counting, or for keeping track of days, or for some other purpose now quiet and hidden from us. Scholars study these objects carefully, but they do not always know exactly what each mark meant. A row of notches may look like a number, but the full story of the hand that made it has passed away. Still, the marks remind us of something simple and human. People wanted to remember, they wanted to compare, they wanted to know whether the herd was complete, whether the storehouse was full enough, whether a promise had been kept. In a small settlement, near a low fire glowing in the evening, grain might be poured slowly into a clay jar. The sound would be soft and dry, like rain made of seeds. A family or a group might need to know how many jars were filled before the cold season came. If one jar was filled, a token might be placed in a basket. If another jar was filled, another token joined it. The tokens did not look like grain, and they were not grain, but they helped hold the thought of grain. This is one of the gentle beginnings of mathematics, a thing standing for another thing. A pebble could stand for a sheep, a notch could stand for a day, a nut could stand for a bundle. The world was full of things that could be counted because they were present. They could be touched, seen, lifted, carried, eaten, exchanged, or remembered. Counting answered the question, how many are here? And for a very long time, that was enough. If there were sheep in the pen, they could be counted. If there were no sheep in the pen, a person did not need a special number written down. They could say in whatever language they spoke, there are none. They could gesture toward the empty space. They could leave the place in the record blank, if there was a record at all. Every day nothing is very old. People have always known what it means for a basket to be empty, for a hand to hold no stones, for a path to have no footprints after rain, a missing tool, an empty jar, a silent field after harvest. These are simple kinds of absence. No one needed advanced mathematics to understand them, but mathematical zero is something different. Zero is not only the feeling of an empty hand. It is not only the word none. It is a written number, a symbol that can sit beside other numbers and change how they are read. It can take part in calculation. It can mark an empty place inside a number. It can mean a starting point, a balance, or a quantity of nothing. That idea came much later. In these early worlds, numbers were often tied to things. A count of 5 might mean 5 goats, 5 fish, 5 shells, or 5 days of travel. A count of 10 might mean 10 fingers, 10 pots, or 10 people gathered near a fire. The number was often connected to a practical need. A hunter might remember how many arrows remained. A gatherer might divide fruit among children. A maker of tools might count blades of stone. A traveler might mark the days between one river and the next. When goods were exchanged, counting became especially useful. If one family gave baskets of grain and expected hides in return, both sides needed some way to remember the agreement. A debt is also a kind of count. It is a promise stretched across time, something given now, something returned later. To keep such promises clear, people needed memory, and memory was helped by signs. In some places, small clay tokens were shaped and used to represent goods. A cone, a sphere, or another simple form might stand for a measure of grain or an animal. These tokens could be counted, stored, sealed, and compared. They were quiet little objects, but they carried meaning. There is a peaceful steadiness in this kind of counting. It does not rush. It moves one by one. A hand reaches into a pouch. A stone is placed on the ground. Another follows, then another. The small pile grows, and with it grows certainty. In the beginning, counting did not need a symbol for an empty place. It needed signs for things that were there. One basket, two baskets, three baskets, a full jar, a herd returning at dusk, a row of fish drying near the shore, a bundle of reeds, a circle of people. When nothing was there, the absence could remain unmarked. The empty pen spoke for itself. The unused bowl needed no sign. The blank space could simply be blank. Yet human life was changing. Villages became larger. Storehouses held more goods. Fields were measured. Trade reached farther. Promises became more numerous. Memory, though powerful, needed help. A shepherd could remember a small flock, perhaps, but a town needed records. A household could count jars by looking at them, but a storehouse needed marks that would remain after the door was closed. Little by little, counting moved from the hand to the surface, from fingers to marks, from stones to tokens, from memory to record. And once people began writing numbers down, a new question slowly appeared. Not just how to count what was there, but how to show what was missing in the middle of a written number. How to make a blank place visible. How to let an empty space be read correctly by someone else. That question did not arise all at once. It waited patiently, like a seed in dry ground. For now, the story rests with the first counters, people of practical wisdom sorting the world gently into one and another and another. They counted animals at dawn, jars at dusk, days beneath the changing moon. They used stones, fingers, knots, tokens, and marks, each simple sign holding a small piece of order. And as the firelight lowered and the counted things were gathered in, the idea of zero was still far away, not forgotten, not rejected, simply not yet needed. But the marks would grow more lasting. The records would grow more careful. The small token would lead toward the tablet. The stone in the hand would become a sign pressed into clay. And there in the cool surface of damp earth, the next part of Zero's story would quietly begin. Chapter 2. Marks in Clay. The Need for a Placeholder. In the warm lands between the Tigris and Euphrates rivers, where water moved through fields and reeds grew tall along the banks, people learned to keep careful records. There were baskets of barley to count, jars of oil to remember, sheep to list, workers to feed, and goods to exchange. A farmer might bring grain to a storehouse. A shepherd might deliver animals to a temple estate. A merchant might send cloth, metal, or dates from one town to another. In such a world, memory alone was not always enough, so people made marks. Before many records were written as words, small clay tokens were used for counting. A little cone might stand for one measure of grain. A sphere might stand for another kind of good. These tokens could be held in the hand, gathered in a pouch, or sealed inside a clay container. They were simple, useful objects, shaped from the same earth that lay beneath the fields and river banks. Over time, the tokens and marks became part of a larger art of record-keeping. In ancient Mesopotamia, including Sumer and later Babylon, scribes developed ways to write numbers and words on clay tablets. A scribe would take damp clay, press it flat, and smooth its surface. Then, with a reed stylus cut from river plants, the scribe would press signs into the clay. The marks were often wedge-shaped because the end of the reed made a small triangular impression. Row by row, the signs appeared, like tiny footprints crossing a soft field. In a quiet room, perhaps lit by an oil lamp, a tablet might record how much grain had entered a storehouse. Another might list wages. Another might preserve a contract, a calculation, or a lesson for a student learning the craft. When the writing was finished, the tablet could be left to dry in the sun. Some tablets were baked hard by accident or by intention, and so they survived for thousands of years, carrying their small marks into our own time. These marks in clay were more than simple lists. Mesopotamian scribes became highly skilled with numbers. They measured fields, divided goods, calculated interest, and worked with tables of multiplication and reciprocals. Their mathematics was practical, but also subtle and sophisticated. One of their important tools was a place value system. Place value means that the position of a sign changes its value. We use place value every day without needing to think about it very much. In our modern decimal system based on 10, the symbol 2 can mean different things depending on where it stands. Written by itself, 2 means 2. In 20, the same symbol means 2 tens. In 200, it means 2 hundreds. The mark is the same, but the place gives it a larger or smaller meaning. Mesopotamian scribes used a different base. Babylonian mathematics used a base 60 system called sexagesimal. Sexagesimal simply means based on 60. Instead of grouping numbers mainly by tens, as we do, the Babylonians grouped them by 60s. This may sound unusual at first, but traces of base 60 are still with us. We count 60 seconds in a minute and 60 minutes in an hour. A circle is often divided into 360 degrees, which is 6 groups of 60. In this quiet way, a very old number system still sits inside clocks and circles today. The Babylonian system was not exactly like our modern decimal writing. Its signs and habits were different. But it did share the deep idea of place value. A mark could mean one amount in one position and a much larger amount in another. Place value is powerful because it lets people write very large numbers with relatively few signs. Instead of inventing a new symbol for every larger quantity, a scribe could let position do some of the work. The place of the sign carried meaning gently and silently. But place value also brought a new difficulty. What should be done when a place was empty? Imagine writing a number where one position has something in it, the next position has nothing, and the next position has something again. If the empty place is not marked, the written number may become unclear. In our system, the difference between 22, 202, and 2002 is easy to see because 0 holds the empty places. The 0 tells us there are no tens here or there are no hundreds here. It keeps the other digits standing in the correct positions. Without such a sign, the written number could be misunderstood. The same kind of problem appeared in Babylonian writing. Since the value of a mark depended on where it stood, a missing position could confuse the reader. Was a group of signs meant to stand close together? Was there an empty place between them? Did the number mean one thing or another thing much larger? For a long time, context could help. A trained scribe might understand from the situation what a number was likely to mean. If a tablet concerned a small measure of grain, one reading might make sense. If it concerned a large field or an astronomical calculation, another reading might be intended. But context was not always enough. So gradually, Babylonian scribes began to use special placeholder marks. A placeholder is a sign that shows an empty position in a number. It does not necessarily mean 0 as a full number. It simply says, this place is empty, but do not close the gap. In Babylonian notation, the placeholder was often written as 2 small wedge-like signs. These wedges could sit inside a number to show that one sexagesimal place had no value in it. They helped keep the surrounding signs in their proper places. It was a quiet development, not a loud one, just a small mark in clay, a sign for an empty place. And yet it mattered. The placeholder did not count sheep. It did not measure grain by itself. It did not yet behave like the number 0 in the way we now use 0 in arithmetic. A Babylonian scribe was not usually adding, subtracting, or multiplying this placeholder as if it were a number with all the modern rules. It was not quite 0 yet. Still, it was an important step. It showed that absence could be written. It showed that an empty place inside a number could be given a visible sign. Nothing in that one position could be marked so that the rest of the number would remain clear. On a clay tablet, among rows of wedges and lines, the placeholder did its modest work. It prevented confusion. It held open a space. It helped a number say exactly what it meant. Perhaps a student scribe learning in a tablet house pressed these signs again and again into practice clay. The room would be still, except for the soft touch of reeds against damp earth. Outside, sunlight might fall across drying tablets. Inside, the student would learn that every mark had its place, and that sometimes even an empty place needed a mark of its own. In time, these habits of writing and calculation helped support many kinds of work. Storehouses could be counted more carefully. Fields could be measured more reliably. Tables of numbers could be copied and used. The clay tablets held not only goods and accounts, but patterns of thought. And as evening came over Mesopotamia, the same careful numbers began to travel beyond the counting room. They moved toward rooftops and open courtyards, where watchers lifted their eyes from clay to sky. There, under the slow paths of the moon and planets, empty places in numbers would become useful in another way, helping patient observers record the rhythms of the heavens. Chapter 3: Empty Spaces Under the Stars. On a flat rooftop in ancient Babylon, the night air cools after the heat of the day. Below, the city settles into quieter sounds. A doorway closes softly. A small lamp burns with its flame shielded from the wind. Nearby, a clay tablet rests within reach, its surface prepared for marks from a reed stylus. Above the rooftop, the sky opens wide. There are no telescopes here, no glass lenses pointing toward the planets. Only the human eye, patient and trained, follows the slow movements of the heavens. The moon rises, changes shape night by night, and returns again. Bright planets wander among the fixed stars. Certain stars appear with the seasons. Eclipses, rare and striking, are remembered, recorded, and studied. Babylonian scholars became careful watchers of these patterns. They observed the moon, the planets, eclipses, and the turning of the year. Their astronomy was not separate from daily life in the way we might imagine today. It was connected with calendars, religious practice, agriculture, and the needs of rulers and cities. To know the sky was also to help mark time, and time, like trade and grain, needed numbers. A farmer might count sacks of barley, a merchant might count jars of oil, a scribe might record silver, land, or livestock, but the astronomer counted in another way. The astronomer counted days between events, positions in the sky, lengths of cycles, and repeated intervals. The moon did not move randomly. The planets did not wander without pattern. With enough watching, enough recording, and enough comparison, patterns could be seen, so the numbers had to be clear. The Babylonians used a number system based on 60. This is called sexagesimal, a word that simply means based on 60. It may sound unusual at first, because many of us are used to a system based on 10. We count with 10 digits, from 0 through 9, and then we begin again in a new place, 10, 20, 100, and so on. But 60 is a very useful number. It can be divided evenly in many ways, by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made it helpful for calculation, especially when dividing measures into smaller parts. A quiet trace of Babylon's base 60 system is still with us. We divide 1 minute into 60 seconds. We divide 1 hour into 60 minutes. We divide a circle into 360 degrees, which is 6 times 60. Every clock face, every careful measurement of an angle, carries a faint memory of those old habits of counting. On the rooftop, a scholar might watch the moon move against the background of stars. On another night, the same scholar, or another like him, might compare the new observation with older records. A tablet could hold numbers from years before. Another tablet might contain a table of predicted positions. Over time, these tablets formed a kind of memory outside the mind, rows of marks, patient and durable, pressed into clay. The marks themselves were small, angular impressions made by a reed stylus. In soft clay, the stylus left wedge-shaped signs. The tablet might then dry and harden, keeping its record through seasons, years, and sometimes centuries. Yet as the numbers grew more complex, a difficulty remained. In a place value system, the position of a mark matters. A sign in one position may mean one amount. The same sign in another position may mean 60 times as much, or 60 times 60. The value depends on where the mark stands. This is familiar in our own way of writing numbers. The digit 3 means 3 in the number 3, but in 30 it means 3 tens. In 300, it means 3 hundreds. The shape is the same, but the place changes the value. The Babylonians had a place value system too, though it was based on 60 rather than 10, and in such a system an empty place can cause confusion. If a number has a missing position, how should the reader know? Is the mark meant to stand close to another mark? Or is there a silent gap between them? Does the number mean one thing, or something much larger? A blank space can be useful when everyone understands it. But over time, across tablets, across scribes, and across long calculations, silence can become unclear. So Babylonian scribes developed a way to mark that empty position. They used a placeholder, often described as a pair of small wedge-like signs. A placeholder is not a number in the full modern sense. It is a sign that says, "There is an empty place here, do not overlook it." It was a small mark for absence, not a number to count with, not yet a zero that could be added or subtracted. But still it was important. It made emptiness visible in the written number. It gave the reader a guide through the rows of signs. In astronomical records, this mattered deeply. The sky returns, but not in the simple way a footstep returns on a path. The moon's cycle, the year, the motion of planets, and the timing of eclipses all require careful measurement. A slight mistake in a number could lead to confusion in a table. A missing place could alter the meaning of a calculation. The placeholder helped protect the shape of the number. Imagine a tablet under the dim light of a guarded lamp. The observer has recorded a position, a time, or an interval. The clay is still damp enough to receive another sign. The stylus presses down, making one wedge, then another. The small pair of marks does not stand for sheep, or jars, or days. It stands for an empty position inside a number. Something absent has been given a sign. There's a quiet beauty in that step. The Babylonians did not yet have zero as later mathematicians would understand it. They did not use this placeholder as a full number with complete rules of arithmetic. It was not the same as the zero we write today. It was more limited, more practical, tied to notation and clarity. But it was still a step toward a larger idea. Before, an empty place might have been left to spacing, memory, or context. Now it could be shown, it could be written into the structure of a number. The absence was no longer merely silent. It had a small mark. The moon continued its slow path. The planets continued their wandering. The seasons returned. Tablets gathered in archives and study rooms holding columns of numbers and observations. The work was patient. It belonged to many hands and many years. And in that patient work, mathematics learned something gentle and powerful. Sometimes what is not there must still be recorded. Later, other cultures would ask broader questions. They would wonder not only how to mark an empty position in a number, but what emptiness itself might mean. Could nothing be spoken of as something? Could absence have a name? Could a sign for nothing become a number in its own right? For now, beneath the Babylonian stars, the answer was practical and quiet. A missing place had found its mark. The sky was wide, the clay was cool, and the small wedges rested among the numbers like a pause made visible. Chapter 4. Nothing in Words, Philosophies of Emptiness. In a shaded courtyard, where sunlight moved slowly across a tiled floor, a few people sat with scrolls unrolled beside them. The air was warm, softened by stone walls and the leaves of olive trees. Sandals made quiet sounds on the ground. A cup of water rested near a low table. Somewhere nearby, a pen waited beside a sheet of writing. Here, numbers were not only tools for counting grain or measuring land, they could also become part of a larger question. What is a point? What is a line? What is space? And if a place holds nothing at all, is that nothing somehow real? These were the kinds of questions that belonged to philosophy. Philosophy means careful thinking about large matters, being, knowledge, nature, change, and the hidden structure of the world. It is not only argument, though people often discussed and debated. It is also a patient form of wondering. Long before zero became a familiar number, people everywhere understood absence in ordinary life. A jar could be empty, a field could have no sheep in it, a hand could hold no stones, a debt could be paid until nothing remained. In daily speech, nothing was simple enough. It was the absence of something expected. But mathematical zero asked for something more delicate. It asked people to write nothing as a mark. It asked them to let an empty place take part in calculation. It asked absence to become visible. Not every tradition needed that idea in the same way or at the same time. In the Greek-speaking world, thinkers gave much attention to shape, proportion, and space. Greek mathematics grew especially strong in geometry, the study of figures, circles, triangles, lines, angles, and solids. A geometer might draw a triangle in sand or on a wax tablet, then ask what must always be true about triangles, not just this one drawn triangle. From such quiet drawings came deep ideas about proof, measurement, and form. Greek mathematicians made remarkable discoveries without using zero as a standard number. They studied ratios, areas, curves, and the relationships between lengths. They explored the properties of circles and spheres, the behavior of light, and the paths of heavenly bodies. Their mathematics was not incomplete simply because it did not follow the later road of zero. It was a different road, carefully paved. Their numeral systems also shaped what felt natural. Greek numbers were often written with letters of the alphabet, rather than with a positional system like the one used by the Babylonians or the decimal place value system that would later grow in India. In a positional system, the location of a symbol changes its value. In our modern writing, the 2 in 20 means 2 tens, while the 2 in 200 means 2 hundreds. That kind of writing creates a strong need for a placeholder, a sign that says this place is empty. Greek numerals did not usually work in that way. Because of this, there was less practical pressure to create a written zero. Calculations could be done with counting boards, geometric reasoning, or other methods. The absence of zero was not merely a philosophical hesitation. It also came from habits of writing and calculating. Still, the idea of nothing was present in thought. Some Greek philosophers debated whether a true void could exist. A void means empty space, a place with nothing in it. The question sounds simple, but it opened into many paths. If there were a complete emptiness, what would it be? Could something move through it? Could a place exist if it contained no matter? Is emptiness a kind of thing, or only a word for the absence of things? Different thinkers answered in different ways. Some imagined empty space as necessary for motion. Others were cautious. In the Aristotelian tradition, named for Aristotle, the idea of a true void was often treated with suspicion. Aristotle's picture of nature did not welcome completely empty space. For him, and for many who followed him, nature was full, ordered, and continuous. A place with absolutely nothing in it seemed difficult to accept. This was not foolishness. It was careful thought within a particular understanding of the world. People were trying to explain motion, matter, change, and the heavens, using the tools of observation and reasoning available to them. Their questions were serious, and their answers often subtle. It is easy from a later time to imagine that zero was waiting plainly in front of everyone, like a small circle already drawn on a page. But ideas do not appear in every culture in the same form. A society may have empty jars, empty rooms, and words for nothing, while still not making nothing into a number. A mathematician may understand absence, yet not need a symbol for an empty position. A philosopher may discuss the void for a lifetime without writing zero into arithmetic. So the story of zero moves gently, not by judging one tradition against another, but by noticing how each approached emptiness in its own way. In Greek astronomy, there were moments when a zero-like mark did appear. Claudius Ptolemy, writing in Greek in the 2nd century CE, created important astronomical tables. These tables helped describe the positions and motions of heavenly bodies using the inherited sexagesimal system, the base 60 system that had long been used in Babylonian astronomy. Sexagesimal means based on 60. Its traces remain with us whenever we count 60 seconds in a minute, 60 minutes in an hour, or divide a circle into 360 degrees. Astronomers found this system useful because 60 can be divided evenly in many ways. When Ptolemy wrote astronomical numbers in this system, he sometimes needed to show that a certain place was empty. For this, he used a small circle-like sign in his tables. It marked an empty sexagesimal place, much as the Babylonian placeholder had done before. A small round sign appeared where nothing stood. It was a beautiful and important step, yet it was still closer to a placeholder than to zero as a full number. It helped keep positions clear in a written number. It did not become in Greek mathematics a number with complete arithmetic rules of its own. It was a sign for an empty place, not yet the quiet number that could be added, subtracted, and multiplied in the way zero later would be. Even so, one can imagine the page, columns of figures, careful astronomical entries, the small round mark set among other signs. Outside, perhaps, the moon lifted over the horizon. The sky turned darker. A scholar checked a table by lamplight, following the slow motions of planets through ordered rows of numbers. The mark was modest. It did not announce a revolution. It simply helped a table say what needed to be said. Here, in this place, there is no amount. Across the ancient world, absence had many meanings. It could be a philosophical puzzle, a practical gap, a silent place in a number. The Greeks explored being and nothingness, with words and arguments. They explored space with lines and figures. They gave mathematics forms of clarity that would last for centuries, but zero as a number was still waiting for another setting. The story now turns toward warmer courtyards, palm leaf manuscripts, and ink drying in quiet strokes. In India, a word meaning empty, shunya, would enter mathematics in a new and lasting way. There, the empty place would slowly become a written sign, and the written sign would become a number. Chapter 5: India and the Number That Meant Nothing. Warm air rests over a quiet courtyard. A palm leaf manuscript lies open in the afternoon light, its long, narrow surface prepared for careful writing. Nearby, a scholar dips a pen into dark ink. The hand moves slowly, placing signs in a line. One mark for a number, another mark beside it, and then, in a space that might otherwise be empty, a small dot. It is a tiny thing, only a dot, or in other places, a small circle. Yet this little sign belongs to one of the great turning points in the story of numbers. In India, over many centuries, mathematicians developed a way of writing numbers that would become deeply important to the world. It was a decimal place value system. Decimal means based on 10, as in the 10 fingers that have helped people count for a very long time. Place value means that the position of a numeral changes what it means. A numeral is simply a written symbol for a number. In such a system, the same sign can mean different amounts depending on where it stands. A 5 may mean 5 ones. Moved one place to the left, it may mean 5 tens. Moved another place, 5 hundreds. The value grows or shrinks according to position. This is a gentle idea, but a powerful one. It allows numbers to be written compactly. It lets a small group of symbols describe very large amounts, but it also creates a quiet need. If a position has no value in it, that empty position must still be shown somehow. Without a sign for the empty place, a number can lose its shape. So a mark was needed, a small mark for absence, a sign that said, there is nothing in this place, but this place still matters. In India, this sign did more than hold a position. Over time, it also became a number in its own right. The Sanskrit word often connected with zero is shunya. It means empty, void, or nothing. Sanskrit was a learned language of ancient India, used in scholarship, poetry, philosophy, and sacred texts. The word shunya carried a sense of openness, absence, or emptiness. And in mathematics, that idea of emptiness found a useful written form. A dot could mark it. A little circle could mark it. Something small could stand for nothing. This was not the work of one person on one particular day. Zero was not invented all at once, like a tool lifted newly from a workshop bench. It developed gradually, through writing, calculation, teaching, and thought. Many hands copied manuscripts. Many minds considered how numbers should behave. Many practical needs encouraged clearer ways of recording quantities. India's role was central, because here zero came to be both a placeholder and a number that could be used in arithmetic. Arithmetic means basic calculation, such as adding, subtracting, multiplying, and dividing. Earlier cultures had made important steps toward writing empty places. Babylonian scribes, for example, had used placeholder marks in their base 60 system. But in Indian mathematics, the empty place moved towards something more complete. It became part of the family of numbers. One can imagine a teacher explaining a written number to a student in a shaded room. The numerals stand in their places. The rightmost place holds ones. The next place holds tens. The next holds hundreds. If there are no tens, the sign for zero keeps that place from disappearing. It keeps the hundreds from sliding too close to the ones. It preserves the pattern. And then, little by little, the student may learn that this sign is not only an empty space. It can be spoken of. It can appear in rules. It can be added or subtracted. It can be part of calculation. By the 7th century CE, Indian mathematicians were treating zero as a number that could enter arithmetic. This was a profound step, though it may have felt quiet at the time. A sign for nothing had become something one could reason with. The evidence for the early history of zero in India comes from different kinds of sources, and some of them are still discussed by scholars. One famous example is the Scoli manuscript, an old mathematical text written on birch bark. It contains dots used as zero-like placeholders. The manuscript is important and fascinating, but its dating is complex and debated. Parts of it may come from different times, and scholars continue to study exactly how old its layers are. So in speaking of the Scoli manuscript, it is best to be careful. It shows us an important use of a dot as an empty place marker, but it is not a simple answer to the question, where did zero begin? History often does not give one single beginning. It gives traces, it gives fragments, it gives marks on bark, ink on leaves, inscriptions on stone. Another important trace appears at Gwalior in central India. The Gwalior inscription, dated to 876 CE, is often cited as one of the earliest secure examples of zero written as a numeral in a decimal place value context. There, carved into stone, a small round sign helps record a number. The stone has stood through sunlight and shadow, through seasons of heat and rain, and among its carved words and figures is evidence of a way of writing numbers that would travel far. The zero in such an inscription is not merely a blank. It is not silence left by accident. It is a deliberate sign. It belongs to a system. It helps the number mean what it is meant to mean. In the late afternoon, temple stone grows warm beneath the lowering sun. A carved mark rests quietly within a line of writing. People may pass by without pausing over it. Yet that little circle is part of a much larger human story. The story of learning to give shape to absence. Indian mathematical thought did not grow apart from ordinary life. Numbers were useful in trade, astronomy, poetry, architecture, ritual calendars, land measurement, and teaching. A strong notation made calculation easier. A decimal place value system with 9 numerals and a sign for zero allowed people to write numbers clearly and work with them efficiently. The 9 numerals named amounts from 1 through 9. The zero held an empty place, and then became an amount, none. Together they formed a flexible written language for number. A number such as 105 depends on zero. The 1 tells us there is 100. The 5 tells us there are 5 ones. The 0 tells us there are no tens. Without it, the number might be mistaken for 15, or something else entirely. 0 keeps the structure open and honest. It says, here is a place, and it is empty. There is a quiet beauty in that. To mark emptiness is not to ignore it. It is to notice it clearly. Far across the ocean, in Mesoamerica, another culture also found a way to write an empty place. The Maya developed a zero-like symbol independently. Their number system was based on 20, rather than 10, and their zero was often shaped like a shell. It was especially important in calendar calculations, helping to mark positions and cycles of time. One may picture sun-warmed stone after rain, painted codices folded like screens, and a shell-shaped sign resting among dots and bars. The Maya zero did not directly become the zero used in the modern global numeral system. Its path was separate, but it reminds us that the need to mark absence can arise in more than one place, under different skies, in different languages, for different purposes. Human beings watched days pass. They counted cycles of the moon and sun. They stored grain, measured land, traded goods, and wrote down time. Again and again, the empty place asked to be seen. In India, that empty place took on a special mathematical life. The word shunya gave language to emptiness. The written dot or circle gave it form. The decimal system gave it a position. Arithmetic gave it action. A small sign could now say, there are no tens here. It could also say, the amount is none. It could stand in a calculation and leave another number unchanged. It could become the quiet center around which later rules would gather. The story does not pause here as if everything were finished. Zero still had to be studied, explained, and carried into other languages. Its rules still had to be written carefully. Some questions would be simple. Others would be difficult. What happens when zero is added? What happens when it is subtracted? What happens when it is multiplied? And what strange trouble appears when someone tries to divide by zero? For now, the small dot rests on the manuscript. The ink dries slowly. The courtyard grows cooler as the light softens. No longer merely an empty place, zero waits calmly among the numerals, ready to enter calculation. Chapter 6. Rules for the Quiet Number. Filtered light falls across a quiet room. A scholar's hand moves slowly over a manuscript, guiding a dark line of ink along the pale surface of a palm leaf. The leaf has been smoothed and prepared. The writing is careful. Each mark has its place. Around the page there is stillness. The pause before a thought becomes a sign. The calm moment before a rule is written down. By now, 0 has become more than an empty space in a number. In India, it has begun to take on a fuller life. It can hold a place, yes. It can show that there are no tens in a number, or no hundreds, or no ones. But it can also be treated as a number in its own right. A number for none, a small sign for nothing, a quiet number that can enter calculation. Calculation with numbers is called arithmetic. Arithmetic is the familiar work of adding, subtracting, multiplying, and dividing. It is the mathematics of baskets and coins, of fields and measures, of debts written down and goods counted carefully. It can be simple, like adding 2 jars of grain to 3 jars of grain. It can also become subtle, especially when the number being used is 0. In the year 628 CE, an Indian mathematician named Brahmagupta wrote an important work called the Brahmasphruta Siddhanta. The title is long and musical, and the work itself was concerned with astronomy and mathematics. In its pages, Brahmagupta gave rules for using 0 in arithmetic. This was a major turning point. He did not make 0 appear out of nowhere. Ideas of empty places and 0-like signs had been developing over time, but Brahmagupta's work gave 0 a clearer role in calculation. He described how 0 behaved when placed beside other numbers, and how it acted when added, subtracted, or multiplied. These rules can be spoken very gently. A number plus 0 stays the same. If you have 5 lamps in a courtyard, and no more lamps are added, there are still 5 lamps. Nothing has joined them. The number is unchanged. A number minus 0 also stays the same. If there are 5 lamps and none are taken away, 5 remain. Nothing is left. Again, the number is unchanged. A number minus itself is 0. If 5 lamps are there, and 5 lamps are removed, none remain, the place is empty. The count has come to 0. 0 times a number is 0. If there are no baskets, and each basket holds 7 fruits, then there are no fruits in those baskets. However many each basket might have held, there are no baskets to hold them. The answer is 0. These rules may sound simple now. They may seem almost obvious, like noticing that a quiet room remains quiet if no new sound enters it. But to write them as rules was a profound step. It meant that 0 was not merely a blank. It was not just a gap between other marks. It could be used. It could take part in the orderly language of numbers. Brahmagupta also wrote about positive and negative numbers. A positive number is a number greater than 0. A negative number is a number less than 0. To explain them, Indian mathematicians often used everyday ideas such as fortunes and debts. A fortune was something possessed, something gained. A debt was something owed, something that pulled the count below balance. If a person had a fortune of 10 and a debt of 3, one could think of what remained. If debts were greater than fortunes, the amount might pass below 0, into the world of negative numbers. This was another quiet widening of mathematical thought. 0 stood between the two directions. On one side were positive numbers, amounts above nothing. On the other side were negative numbers, amounts below nothing, like debts waiting to be repaid. 0 was the balance point, the place where fortune and debt met evenly. Imagine a line drawn softly across a page. In the center is 0. To the right, the numbers grow, 1, 2, 3, and onward. To the left, the numbers descend, -1, -2, -3, and onward. The line itself may not have been drawn in exactly this modern way by Brahmagupta, but the idea of numbers above and below 0 was beginning to find a language. 0 became a meeting place, a point of balance, a sign that said, here, the account is even. And yet not every question about 0 was easy. There was one operation that remained especially difficult: division by 0. Division is the act of sharing or grouping. If 12 fruits are divided among 3 baskets, each basket receives 4 fruits. If 12 fruits are divided among 6 baskets, each basket receives 2. Division asks in a simple way, how much is in each part? But what would it mean to divide by 0? What would it mean to divide 12 fruits into 0 baskets? There are no baskets to receive them. No groups have been made. The question no longer behaves like ordinary sharing. It does not lead to a clear answer in standard arithmetic. Brahmagupta wrote about division involving zero, but these rules were not fully correct in modern terms. Later Indian mathematicians also returned to the question. One of them, Bhaskara II, writing centuries later, discussed division by zero and sometimes connected it with infinity. Infinity is the idea of endlessness, something without a final boundary. It is not an ordinary counting number like 3, 10, or 100. It is a large and subtle idea, and its relationship with zero has often invited deep thought. But in standard modern arithmetic, the rule is calm and clear. Division by zero is undefined. That means it has no accepted answer within the usual rules of arithmetic. It is not simply a very large number. It is not a number that can be written down in the ordinary way. The operation does not fit. There is no need to force it. Some questions in mathematics ask us to be careful. They show us where a rule works and where it must stop. This too is part of the story of zero. Not only what it allows, but also what it asks us to define with care. In the quiet room, the manuscript grows line by line. There are rules for numbers, rules for the sky, rules for calculation. The scholar's hand pauses, then continues. Ink darkens as it dries. The palm leaf holds the marks patiently. Zero, once an empty place, has become a participant in thought. It can be added, and nothing changes. It can be subtracted, and nothing changes. It can appear when a number is taken from itself. It can multiply everything back into stillness. It can stand between fortune and debt. It can mark a balance. And when a question becomes too delicate, as with division by zero, it reminds mathematicians to move with care. This carefulness is one of the quiet beauties of mathematics. It is not only a matter of answers, it is also a matter of knowing what a question means. A symbol must be understood. A rule must be tested. A small mark must be given its proper place. From such patience, ideas travel. A manuscript may be copied by another hand. A rule may be taught to a student. A sign may be written again on a new page, then carried to another town, another court, another library. The zero that had settled into Indian mathematics did not remain still forever. It became portable. It could be copied in books, spoken in lessons, used in accounts, and carried along roads where merchants and scholars traveled. Its small shape, whether dot or circle, could move easily across a page. Its meaning could be explained, practiced, and remembered. A sign for nothing had become useful enough to journey. And so, in time, the quiet number would begin to travel westward through trade, translation, and study into new languages and new hands. Chapter 7. A small circle travels west. In the soft light of evening, a caravan moves slowly across open land. The camels step with patient rhythm. Their bells make a low, gentle sound, rising and falling with the motion of the road. Bundles are tied carefully to their sides. Cloth, spices, metalwork, books, letters, and sheets of paper wrapped against dust and weather. Along with goods that can be weighed and touched, other things travel too. Words travel, methods travel, quiet ideas travel from one hand to another. Among these traveling ideas was a way of writing numbers. It had grown in India over many generations. 9 numerals, a place value system based on 10, and a sign for 0. This system could write small numbers and very large numbers with graceful economy. The same symbols could shift their value depending on where they stood. A mark in one place might mean 2, in another place 20, in another 200, and when a place was empty, there was a sign for that too, a small mark, an empty place, a sign for nothing that helped the rest of the numbers speak clearly. As merchants moved along roads and ships crossed seas, this way of writing numbers moved with them. It did not travel in a single straight line, like an arrow shot from one place to another. It traveled more like water through channels, branching and joining, pausing in one city, flowing onward to the next. It moved through trade, through scholarship, through translation, and through the ordinary conversations of people who needed to count, measure, record, and calculate. This movement of an idea from one place or culture to another is called transmission. Transmission does not mean that an idea is simply carried unchanged, like a sealed jar. More often, an idea is opened, studied, adapted, renamed, and made useful in new surroundings. The sign changed shape. The idea remained useful. In the centuries after the rise of Islam, Scholars across a wide region studied the learning of many peoples. In cities of the Islamic world, knowledge from India, Greece, Persia, and other traditions was read, translated, compared, and expanded. Astronomical tables, medical writings, philosophical works, and mathematical texts passed from language to language. Some arrived in Sanskrit, some in Greek, some in Syriac or Persian, and many were then rendered into Arabic, the language of scholarship across much of this world. In a quiet room, one might imagine a scholar leaning over a page. The paper is pale, the ink is dark, a reed pen rests between the fingers. The scholar is not merely copying marks, he is thinking with them. He is asking what they can do, how they can be used, and how they might fit with older methods of calculation. The Indian numerals were among the ideas that drew attention. These numerals, ancestors of the modern symbols 0 through 9, are often called Arabic numerals in Europe, because Europeans came to know them through Arabic-speaking scholars and texts. A more precise name is the Hindu-Arabic numeral system. Hindu here points toward their important development in India. Arabic points toward the scholars and cultures of the Islamic world who studied them, used them, reshaped them, and helped carry them westward. The name itself is a small map of a long journey. The 0 in the system also received a new name. The Sanskrit word shunya, meaning empty or void, was translated into Arabic as sifr. The word sifr also meant empty. It was a good word for a mark that showed an empty place. Sifr, a soft word for absence, a word for an open space in a number, a word that would travel far. As centuries passed, sifr entered other languages. In medieval Latin, it became forms such as zephyrum. In Italian and other European languages, it became words like cifra. From the same source came the English word cipher, which once could mean 0, and later came to mean a code or secret writing. And from this family of words came 0, the familiar name we use today. So the sign traveled and the word traveled with it, changing little by little as it crossed borders of language and script. Shunya became sifr. Sifr became sifra, cipher, zephyrum, and 0. The sound altered. The idea remained. In marketplaces, the usefulness of the numerals was easy to feel. A merchant at dusk might sit beside a low table, checking the ledger after the day's trade. Coins lie in small piles. Measures of grain have been marked. Cloth has been sold by length. A debt is recorded. A payment is subtracted. The page must be clear because tomorrow's business will depend on today's numbers. Older systems could do such work, and many people use them skillfully. Counting boards, finger reckoning, and local numeral traditions all had their place. But the Hindu-Arabic system offered something compact and flexible. With only 10 symbols, including 0, one could write number after number in a neat line. The place of each digit gave it value. The 0 held empty positions so that the other digits did not drift into confusion. A 5 could be 5. A 5 followed by a 0 could be 50. A 5 followed by 2 zeros could be 500. The small circle, or dot, or sign of emptiness did not add a thing you could touch. Yet it changed how the whole number was read. The shapes of the numerals were not fixed as they moved. They changed with handwriting, with regional scripts, with the habits of scribes, and with the tools used to write them. A mark made with a reed pen on paper looked different from a mark carved into stone, or written with a brush. In Eastern Islamic lands, one family of numeral shapes developed. In Western Islamic lands, including North Africa and Al-Andalus in Spain, other forms took shape. These Western forms would later influence the numerals used in much of Europe. So when we look at the digits on a modern page, we are not seeing marks that have always looked exactly this way. We are seeing descendants. Like words in a language, numerals have histories. They carry faint traces of many hands. The sign changed shape. The idea remained useful. It is important to linger gently over this point. Scholars in the Islamic world did not merely store knowledge on shelves, they worked with it. They translated, but they also questioned and extended. They compared Indian methods with Greek geometry, Persian astronomy, and local practices of accounting and law. They wrote new books. They developed new techniques. They taught students, solved problems, and applied mathematics to the needs of everyday life and the study of the heavens. A calculation might serve a merchant. It might help measure land. It might support the making of calendars. It might guide astronomical tables. It might clarify inheritance shares, taxes, or contracts. In such practical matters, clarity was valuable. A number had to mean what it appeared to mean. An empty place had to be marked, not guessed. 0, the cipher, offered a quiet kind of order. There is a peaceful beauty in the way an idea becomes accepted through usefulness. Not all at once, not everywhere in the same form, not without hesitation, but gradually because it helps. A scribe finds that the new numerals make a table easier to write. A teacher finds that students can learn a method step by step. A trader finds that accounts fit more neatly on a page. An astronomer finds that positions and intervals can be recorded with greater care. In this way, the small sign for emptiness entered new habits of thought. Perhaps in one city, it appeared as a dot, in another as a small circle, elsewhere as another mark shaped by a different hand. But whatever its shape, it carried a delicate message. This place is empty, and because it is empty, the other places can be understood. Across desert roads and sea routes, through libraries and counting houses, the numerals moved westward. They passed through languages rich with poetry, law, science, and trade. They were copied onto paper, taught in schools, used in ledgers, and discussed by scholars who saw in them not only convenience, but possibility. The journey was slow, and it was shared by many people whose names are not always remembered. Translators, merchants, scribes, teachers, travelers, and students all took part. Some carried books, some carried methods in memory, some simply used the numerals until they became familiar to others. A quiet voice in a marketplace might explain a figure in a ledger. A scholar might write a table by lamplight, a student might practice the shapes again and again. The small circle would be made, erased, and made once more, and so the number that meant nothing continued its journey, becoming part of a larger language of calculation. Ahead lay great centers of learning, where scholars would refine these methods and write books whose echoes would carry into later centuries. In lantern-lit rooms, among pages of ink and patient thought, 0 was ready to become still more deeply woven into the mathematics of the world. Chapter 8: The House of Wisdom and the Language of Calculation. In the evening light of Baghdad, when the heat of the day softened and the courtyards grew cool, lamps began to glow behind carved screens and open doorways. Paper lay stacked on low tables. Reed pens rested beside small pots of ink. A scribe might pause to sharpen the tip of a pen, then return to the page, where dark letters slowly gathered into lines. Baghdad, under the Abbasid caliphs, became one of the great centers of learning in the medieval world. It was a city of markets and gardens, of officials and merchants, of poets, physicians, astronomers, translators, and mathematicians. Ideas arrived there by many roads. Some came with travelers from the East, some came from older Greek works, some came from Persia, Syria, India, and beyond. In quiet rooms, scholars compared languages, copied texts, and worked through problems with patient care. This period is often called the translation movement. A translation movement is a time when many important writings are carried from one language into another. In Baghdad and in other cities, works were translated into Arabic from Greek, Sanskrit, Syriac, Persian, and other languages. Translation was more than changing one word into another. It often meant explaining, adapting, correcting, and expanding. A scholar might read an old astronomical table, compare it with observations, and then write a clearer version. A mathematician might study a method from India and show how it could be used in Arabic. The famous House of Wisdom is associated with this world of translation and learning. Historians still discuss exactly what the House of Wisdom was. It may not have been a university in the modern sense with classrooms and degrees. It may have been a library, a center for translation, a court-sponsored collection of scholars, or several things at once. But as an image, it remains a gentle and powerful one. Rooms of books and papers, careful readers, and lamps burning softly as knowledge passed from hand to hand. And yet Baghdad was not alone. Scholarship in the Islamic world was spread across many cities and regions. Damascus, Cairo, Cordoba, Nishapur, Samarkand, and many other places had their own scholars, libraries, observatories, and schools. Knowledge did not rest in one building or one city. It moved like water through channels, gathering strength as it traveled. Among the scholars connected with Baghdad was Muhammad ibn Musa al-Khwarizmi, who was active in the 9th century. His name would travel far, changing shape as it moved into Latin and then into other European languages. From Latinized forms of Al-Khwarizmi's name came the word algorithm. An algorithm is a step-by-step method for solving a problem. It can be as simple as a recipe. First do this, then do that, then check the result. In mathematics, an algorithm might tell a person how to add two numbers, divide one number by another, or solve a certain kind of equation. It is not magic. It is a path laid out carefully so the mind can follow it. Al-Khwarizmi wrote an influential work on calculation with Hindu numerals, the ancestors of the numerals we now write as 0, 1, 2, 3, and onward. The exact original Arabic text of this work has not survived complete in its earliest form. Much of what is known about it comes through later Latin versions, copied and read in Europe. Even so, its importance is clear. It helped explain how to calculate using a decimal place value system, the system in which a digit's position gives it its value. In such a system, a 5 can mean 5 or 50 or 500, depending on where it stands. A small 0 can hold an empty place, keeping every other digit in its proper position. The 0 does not add weight of its own in a number like 205, but without it, the meaning changes. 205 is not 25. This was one of 0's quiet gifts. It made written numbers compact. It allowed large quantities to be written with only a few signs. It made calculation easier to teach, easier to repeat, and easier to check. A merchant could write a sum in a ledger. A tax official could record amounts owed. An astronomer could arrange numbers for tables of the sun, moon, and planets. A surveyor could measure land and keep the result in a clear form. The older methods were not foolish or useless. Counting boards, finger reckoning, and other systems had served people well for a long time. But Hindu Arabic numerals with 0 in its place gave written calculation a new smoothness. The page itself could become a place where numbers moved. One could line them up, carry, borrow, multiply, and divide with marks of ink rather than with piles of counters. Al-Khwarizmi also wrote a famous book whose title included the word al-jabr. From this word came algebra. Algebra is mathematics that uses symbols and rules to solve for unknowns. At its heart is a simple human question. If some part of a quantity is hidden, how can we find it? Imagine a merchant who knows the total price of several goods, but not the price of one item. Or a family dividing an inheritance according to certain shares. Or a surveyor needing to find a length from other known lengths. Algebra gives orderly ways to work with the known and the unknown, step by step. Al-Khwarizmi did not invent algebra all by himself. Like 0, algebra grew from many roots: Babylonian problem-solving, Greek geometry, Indian mathematics, and the needs of daily administration and trade. But his writing gave clear methods and examples, and it became deeply influential. His work helped shape the language of calculation for centuries. The practical uses of this mathematics were many. Trade needed trustworthy accounts. Inheritance laws required careful division of property. Taxation required records of land, produce, and payment. Land measurement helped define fields, canals, and boundaries. Astronomy required tables and predictions, not only for scholarly interest, but also for calendars and timekeeping. Calendars helped communities mark months, festivals, seasons, and obligations. In each of these tasks, 0 could appear quietly. It might hold a place in a number, it might mark an absence, it might help keep a calculation aligned. It did not announce itself. It simply allowed the other numbers to stand where they belonged. One can imagine a scholar in a lantern-lit room, looking over a page of figures. The paper is smooth compared with clay or wax. The ink is dark and precise. Around him, other readers murmur softly over text from distant places. A pen moves, a calculation is copied, a word from Sanskrit has passed into Arabic. A method from India has met the questions of Baghdad, and local observations share space on the same table. This is how ideas often travel, not as a single bright flash, but through many careful acts. A text is translated, a table is corrected, a student learns a method, a merchant finds it useful, a scribe makes another copy, the copy moves to another city. There another reader adds a note in the margin. 0 traveled in this way too. It was a small sign with a large usefulness. In Arabic it was called sifr, meaning empty. From that word, later languages would form words such as cipher and 0. The sign changed shape as it moved through scripts and regions, but the idea remained: an empty place that could be written, a nothing that helped numbers speak clearly. By the time these methods moved farther west, they carried with them more than symbols. They carried habits of calculation, ways of arranging a page, and confidence that large and difficult numbers could be handled by a steady process. An algorithm could guide the hand, algebra could guide the mind, zero could keep the quiet places open. And so, as lamps dimmed in one library, other lamps were being lit elsewhere. Manuscripts were copied and bundled. Traders packed ledgers among cloth and spices. Scholars carried books across borderlands. Ships waited in Mediterranean harbors, rocking gently at anchor. The small circle, the empty place, the quiet number, was ready to continue its journey toward Latin-speaking Europe, toward counting houses and merchant tables, and toward the next slow chapter in its long human story. Chapter 9. Across the Mediterranean. At the edge of the sea, the harbor water moved quietly against the stones. Small waves touched the piers and slipped away again. Ships rested at anchor, their ropes drawn firm, their wooden sides creaking softly with the motion of the tide. In the morning, merchants would lift bundles from the holds. Cloth, spices, metalwork, paper, jars of oil, and sacks of grain. But in the gentle hour before the day's work, the port was almost still. Across this sea, ideas traveled as steadily as goods. The numerals we now use so easily, 0, 1, 2, 3, and onward, did not arrive in Europe all at once. They crossed by many routes, over many years. They came through trade, through teaching, through translated books, and through the patient work of people who needed to count, measure, and record. Some came through Spain, where Arabic-speaking, Hebrew-speaking, and Latin-speaking scholars lived near one another and worked with texts from many traditions. Some came through Sicily, an island shaped by Greek, Arabic, Latin, and Norman influences. Some came through the ports of the Mediterranean, where merchants listened carefully to one another's methods, especially when those methods made accounts easier to keep. And some came through books. In medieval Europe, many scholars read Latin, but much important mathematics had been written in Arabic, Persian, Greek, Sanskrit, and other languages. So translators became quiet bridges between worlds. They sat with manuscripts and dictionaries, with memory and training, and carried ideas from one language into another. A word, a method, a symbol, each could make the journey. The Hindu-Arabic numeral system, with its 9 numerals and its sign for 0, had already traveled a long way before reaching Latin Europe. It had grown in India, been studied and expanded in the Islamic world, and taken new written forms as it moved through different regions. In Europe it was often called Arabic, because Arabic scholarship helped transmit it westward. More precisely, it belonged to the broader Hindu-Arabic tradition. Its special power was not only in the shapes of the signs, it was in the way they worked together. A single digit could change value depending on where it stood. A 2 might mean 2, or 20, or 200. And 0, the small sign for an empty place, helped hold the other digits in their proper positions. This made written calculation compact and clear. It allowed long numbers to fit neatly on a page. It allowed merchants and scholars to work step by step with ink, parchment, wax tablets, and memory. Still, an idea can be useful long before it becomes familiar. In many European towns, Roman numerals remained common. A number such as VIII or 2XIV was easy enough for many records, especially when people were used to seeing it. Counting boards were also widely used. A counting board was a tool for calculation. It might be a table, a board marked with lines, or a frame with counters or beads. By moving the counters from place to place, a trained person could add, subtract, multiply, or divide. The counting board was practical. It was visible. It could be checked by the eyes and hands. A person could slide counters into rows and columns, and the pattern showed the value. So, for a long time, written numerals and physical calculating tools lived side by side. One method did not immediately replace the other. In shops and offices, in schools and counting houses, people used what they knew. A ledger, a book for keeping accounts, might contain familiar marks, careful notes, and slowly, here and there, the new numerals. Among the people who helped explain the new system to Latin-reading Europe was Leonardo of Pisa, better known today as Fibonacci. He was not the inventor of 0. He was not the only person who brought Hindu-Arabic numerals into Europe. Many travelers, translators, teachers, and merchants helped in that long movement, but Fibonacci became an important voice. He was born in Pisa, a city of ships, trade, and sea wind. His father worked for Pisan merchants in North Africa, in the port of Bujia, now often associated with Bajaya in present-day Algeria. There, as a young man, Fibonacci encountered methods of calculation used by merchants and scholars in the Islamic world. One may imagine the scene gently: a table near a warehouse, light falling through an open doorway, a set of figures written in dark ink, coins counted in small piles, weights checked and recorded, goods measured and priced. Around such tables, numbers mattered, not as distant abstractions, but as everyday tools. How much cloth had arrived? What was the price in one currency compared with another? How should profit be divided? How many measures of grain equaled another local measure? A merchant's work required careful attention. Mistakes could be costly, but good methods could bring order. Fibonacci saw the usefulness of the Hindu-Arabic numerals. They were well suited to the kinds of calculations merchants needed. They could handle large numbers gracefully. They made it possible to write procedures clearly, one line after another. In 1202, Fibonacci wrote a book called Liber Abaci. The title means Book of Calculation. Although the word abaci suggests the abacus or counting board, the book was largely about calculation with the new written numerals. It explained how to use the digits and the place value system. It showed how numbers could be written with the signs 1 through 9, together with 0. It gave practical examples, the sort that would be useful to merchants, money changers, and educated readers. There were problems about currency exchange, showing how one kind of money could be converted into another. There were problems about weights and measures, showing how goods counted in one system could be compared with goods counted in another. There were problems about profit, showing how gains might be shared after a business journey. There were trade calculations, partnership questions, and examples drawn from the ordinary movement of goods across land and sea. The book did not make all Europe change at once. Books moved slowly, learning moved slowly, habits moved slowly, but Liber Abaci helped show that the new numerals were not merely foreign symbols. They were working tools. They could sit beside a merchant's ledger and help keep accounts. They could help compare prices in one port with prices in another. They could help a teacher explain a method, or a student follow a calculation line by line. And quietly, 0 traveled with them. 0 was still a curious sign to many eyes. It was a small circle, a symbol that seemed to stand for nothing. Yet when placed in a number, it changed the meaning around it. In 10, it showed that the 1 stood in the 10's place. In 100, it held 2 empty places. It did not add a visible amount of its own, yet it shaped the value of the whole number, a circle of nothing that meant something. In the Mediterranean world, such ideas often moved without ceremony. A merchant learned a method from another merchant. A translator copied a passage. A teacher made notes in the margin. A student practiced figures on wax, smoothing the surface and writing again. A clerk tested a new way of keeping accounts, then returned to the familiar counting board for another task. No single doorway opened. Rather, many small doors stood ajar. Through Spain, Arabic works became Latin texts. Through Sicily, scholars encountered traditions from several languages. Through ports like Pisa, Genoa, Venice, Marseille, and others, trade brought practical knowledge into daily use. Through North Africa, young Fibonacci saw methods that seemed worth carrying home. The sea connected more than coastlines. It connected habits of thought. And still, the older methods remained. Roman numerals continued to appear in documents, inscriptions, clocks, and official records. Counting boards continued to serve those who knew them well. In many places they were trusted because they were familiar. A person could see the counters. A master could teach an apprentice by demonstration. The hand could move with the mind. The new written numerals offered something different. They allowed calculation to remain on the page. A mistake could be found in a line of figures. A method could be written down and taught from a book. A number could grow long without becoming unwieldy. Neither world vanished in a moment. For many years, and then for generations, Europe held both. On one table might rest a board with counters, on another a parchment ledger marked with the newer digits. In one account a clerk might write Roman numerals. In another a merchant might try the Hindu-Arabic signs. The small 0 waited among them, quiet and patient. It had crossed deserts and libraries, classrooms and markets, languages and alphabets. It had moved from palm leaf manuscripts and scholarly treatises into Arabic texts, then onward into Latin books and merchant practice. It had been translated, reshaped, renamed, and copied. Now it rested in European ledgers beside older marks, useful, but not instantly trusted, clear, but not yet familiar to everyone, a small empty place, ready to help numbers settle into order. Chapter 10: Suspicion, Usefulness, and Slow Acceptance. In a small counting room after market day, the air is quiet. A ledger lies open on a wooden table. Its pages are marked with careful lines of ink. Beside it, a few coins rest in small piles, sorted by value. A candle burns low, and its light moves gently over the written marks. Dust motes drift in the stillness. A bookkeeper bends over the page, checking a sum once, then again, making sure that every number agrees with the goods that pass through the door. By this time, the Hindu-Arabic numerals had begun to appear in Europe. They had traveled through scholars, merchants, translations, and teaching. They had crossed seas and passed through ports. They had been written on parchment, explained in books, and practiced by those who wished to calculate more easily. Yet new tools, even useful ones, are not always welcomed at once. For many people in medieval Europe, the older ways were familiar and trusted. Roman numerals had been used for centuries. They appeared on monuments, in records, in books, and in official writing. A number such as VIII or 12 might seem solid and respectable, because it belonged to a long habit of reading and writing. Counting boards were also widely used. A counting board was a surface marked with lines, where counters could be moved from place to place to represent amounts. It was a practical tool, especially for people trained in its use. Like an abacus, it allowed a person to calculate with the hands as well as the mind. Counters could be shifted, grouped, and removed. A skilled user could work with impressive speed. So when the newer numerals appeared, with their curved and unfamiliar shapes, some people looked at them carefully, and not always with ease. The symbols themselves seemed strange. A 2, a 3, a 5, and especially a 0 did not look like the older marks. Their shapes changed somewhat from region to region and from hand to hand. In a time when many documents were copied manually, and when not everyone could read or calculate fluently, unfamiliar writing could invite hesitation. There was also a practical worry. Hindu-Arabic numerals were compact. That was one of their strengths. But compact writing could also seem easier to alter. A careless or dishonest stroke of the pen might change one digit into another. A mark added before or after a number could change its value. In an account book, where money, grain, cloth, or land might be involved, people wanted records that felt secure. 0 made this concern even more noticeable. 0 was a sign for no amount, an empty place, a nothing, and yet when placed beside other digits, it could change them greatly. A 5 was one thing, a 50 was another, a 500 was larger still. The small round sign did not add a visible quantity of its own, and yet it shifted the meaning of the number around it. To someone trained in place value, this was elegant and clear. Place value means that a digit's worth depends on where it stands. In 5, the digit means 5 ones. In 50, it means 5 tens. In 500, it means 5 hundreds. 0 holds the empty places so the other digits can stand in the right positions. But to someone meeting the system for the first time, this quiet power could feel unusual. How could a mark for nothing do so much? Because of such concerns, some local authorities and institutions restricted the use of Arabic numerals in certain official or financial records. This was not a single sweeping ban across Europe, and it was not a simple story of one group refusing the idea. It was more ordinary than that, and more human. People were cautious with unfamiliar symbols, especially when those symbols appeared in accounts, contracts, and matters of trust. Old methods and new methods lived side by side. In one room, a merchant might use Hindu-Arabic numerals to work out a calculation on scrap parchment, because the method was swift and convenient. In another room, the final record might still be written in Roman numerals, because that was what local custom expected. A clerk might use a counting board to verify a sum, then copy the result into a ledger. A teacher might introduce the new numerals slowly, while students still practiced older forms. This kind of overlap is common in human history. Familiar tools do not vanish simply because newer tools have appeared. A well-used method carries memory in it. It carries confidence. It belongs to the hands of those who learned it long ago. And so the new numerals waited, in a sense. They did not need to win people over all at once. They simply had to be useful. Slowly, usefulness had its own quiet patience. For merchants, the advantages became clear. Trade required many kinds of calculation: prices, debts, interest, weights, measures, currency exchange, shares of profit, and the cost of goods carried over distance. Hindu-Arabic numerals made written arithmetic more compact. They made it easier to set down a problem on a page and work through it step by step. Bookkeeping benefited as well. A ledger is a place where memory is given structure. Goods come in, goods go out, payments are promised, payments are received, balances are checked. Zero had a natural home there, because a balance might be nothing owed, nothing remaining, or nothing gained in a particular column. It could mark absence without leaving the page uncertain. Science also found value in the new notation. Astronomers, physicians, instrument makers, and natural philosophers needed numbers that could be written, compared, and recalculated. The old systems could do many things, but the place value system made long calculations easier to manage. A small circle in the right place could preserve the shape of a number. It could keep the empty column visible. Navigation, too, depended increasingly on careful measurement. Sailors and mapmakers worked with directions, distances, tables, and instruments. No single symbol made navigation possible, of course, but core arithmetic helped people record and use information more reliably. Numbers could travel in books and tables, from one port to another, from one generation of learners to the next. Engineering and building also welcomed efficient calculation. Measuring land, planning structures, dividing materials, and estimating quantities all required practical mathematics. The new numerals gave workers and scholars another way to make numbers portable. They could be written in narrow columns, copied into manuals, and taught by repeated examples. Then came printing, and with printing the spread of written forms became steadier. Printed books could carry the same numeral shapes to many readers. Arithmetic texts became more available. Students could see examples arranged neatly on a page. Teachers could explain methods in a more consistent way. The strange symbols became less strange simply by being seen again and again. Education did what education often does. It turned novelty into habit. A child who learned the digits early would not feel the same unease as a clerk meeting them late in life. The shapes 1, 2, 3, and 0 would become ordinary companions. The idea that 0 held an empty place would become part of the quiet grammar of calculation. What once required explanation would begin to feel natural. Still, the older methods did not disappear immediately. Roman numerals remained on clocks, in inscriptions, in book chapters, and in formal settings. Counting boards and abacuses continued to serve many people. The story was not one of sudden replacement, but of gradual settling. The newer numerals found more and more tasks for which they were especially well suited, and 0, once so odd, became dependable. It could show that no coins remained in a column. It could mark that a place in a number was empty. It could turn 7 into 70, and 70 into 700, not by adding substance of its own, but by helping the other digits stand where it belonged. It was a small circle of nothing that made written numbers clearer. In the hush of the counting house, after the day's bargaining had ended, one can imagine a careful hand closing a ledger. The sums have been checked. The columns are aligned. The ink is dry. Some numbers are large, some small, and some end in 0, that quiet sign which once seemed uncertain and new. Over time, people trusted it because it worked, not all at once, not everywhere in the same way, but gradually through accounts and lessons, through trade and tables, through paper and print. 0 became part of the common language of number. And once it was no longer confined to ledgers, once it had found a place in ordinary calculation, it was ready to travel further still. It could become a point on a line, a balance in an equation, a beginning place on a map of thought. The empty mark had entered daily use. Chapter 11. 0 opens the door to the infinite. A line is drawn softly across a page. It begins as a simple stroke of pencil, pale gray against the paper. At first it seems to be only a mark, quiet and ordinary. But then a hand places one point near the center and writes a small 0 beneath it. From that point, the line stretches in two directions. To the right are the familiar positive numbers. 1, 2, 3, and onward. To the left are the negative numbers, -1, -2, -3, moving away in the other direction. And at the center rests 0, not leaning one way or the other. It is neither gain nor loss, neither forward nor back. It is the balance point. For a long time, 0 had helped people write numbers clearly. It had held empty places in columns. It had allowed merchants, astronomers, and scholars to write large quantities with fewer symbols. It had become a number in its own right, something that could be added, subtracted, and used in rules of arithmetic. But as mathematics continued to grow, 0 became more than a useful sign in calculation. It became a doorway. In algebra, 0 took on a quiet but powerful role. Algebra is the part of mathematics that uses symbols to describe unknown numbers and relationships. Instead of counting only visible things, algebra asks questions such as, what number would make this statement true? Often the answer is found by discovering where something becomes 0. Imagine a scale that balances exactly. Nothing is heavier on one side, nothing is lighter. The difference between the two sides is 0. In algebra, when an expression equals 0, it often means that a balance has been found, or that a hidden value has come into view. A curve may rise and fall across a page. It may cross a line at certain points. Where it crosses, a mathematician may ask, where does this become 0? Those crossing places can reveal answers. So 0 became a marker of solution, a sign that a question had settled into balance. There is comfort in that idea. A number meaning nothing can show where something is true. On another page, a scholar draws two lines, one from left to right and one from bottom to top. They cross at the center. At the crossing point, again there is 0. This point is called the origin. An origin is a starting point on a graph or coordinate system. It is the place from which positions are measured. From there one may move right or left, up or down, near or far. A coordinate is a number or a pair of numbers that tells where something is located. On a flat page, one number may say how far to move sideways, and another may say how far to move upward or downward. Together they guide the eye to a point. In the early modern period in Europe, thinkers such as René Descartes and Pierre de Fermat helped develop coordinate geometry. This was a way of joining geometry, the mathematics of shapes, with algebra, the mathematics of symbols and equations. A curve could be described by an equation. An equation could be drawn as a curve. It was a gentle joining of two worlds, the visible and the symbolic. And at the center of this new map stood 0. 0 marked the origin, the quiet crossing place. From it, numbers could spread in all directions. Positive numbers to one side, negative numbers to the other, up and down, left and right. A page became a landscape of relationships. Negative numbers, too, became easier to imagine with 0 in place. Before such pictures were common, negative numbers could seem strange. How could one have less than nothing? Yet on a number line they found a natural home. If 0 is the middle, then numbers less than 0 can rest on one side, just as numbers greater than 0 rest on the other. A debt can be less than nothing in a purse. A temperature can fall below 0 on a chosen scale. A position can be west of a starting point, or below sea level, or before a certain year in a calendar system. 0 gives such ideas a reference point. It does not explain everything by itself, but it gives the mind a place to stand. Beyond the quiet page, beyond the line and the crossing axes, mathematics kept moving. Curves became important in new ways. Scholars studied falling objects, moving planets, flowing water, changing light. They wanted to understand not only where something was, but how it changed. In the 17th century, Isaac Newton, Gottfried Wilhelm Leibniz, and others developed what we now call calculus. Calculus is a branch of mathematics that studies change and accumulation. It helps describe motion, growth, curves, areas, and many processes in nature. 0 was close at hand in this work, but not in a simple way. Calculus is sometimes imagined as if it were merely dividing by 0, but that is not correct. In ordinary arithmetic, division by 0 has no defined answer. It remains something we do not do in the usual number system. Instead, calculus often studies quantities that approach 0. A step becomes smaller and smaller, a gap narrows, a change is measured over a shorter and shorter interval. The quantity does not need to become 0 in the ordinary sense. It draws nearer and nearer, and the pattern of that nearness reveals something. This leads to the idea of a limit. A limit is a value that something gets closer and closer to. A curve may approach a line without touching it. A sequence of numbers may come nearer and nearer to a certain value. A small change may shrink towards zero, while still helping us understand motion at an instant. It is a delicate idea, like watching dusk deepen by degrees. The change is continuous. The eye follows it gently. The mind notices where it is going. And here, near zero, another great idea appears: infinity. Infinity is the idea of endlessness. It is not an ordinary number that one can count to. It is a way of speaking about something without a final end. Numbers continuing on, space stretching farther than thought can easily travel, a process that never reaches its last step. Zero and infinity are linked in many subtle ways. When numbers become very small, approaching zero, other related quantities may grow very large. A fraction with a smaller and smaller positive bottom number can become larger and larger. A curve may draw close to a boundary and seem to rise without limit. But zero and infinity are not simply opposites. Zero is a number. Infinity is not an ordinary number. Zero can be written on a page, placed on a line, added to another number without changing it. Infinity is an idea of endlessness, treated carefully in different branches of mathematics. Still, the two often appear near one another, like distant stars seen in the same clear sky. One speaks of nothing, balance, or a vanishing amount. The other speaks of no end. Between them, mathematicians learn to describe motion, change, space, and the delicate behavior of curves. In modern science, zero became a trusted reference point. It appears in measurement scales, in equations, and in chosen starting places. A thermometer may mark zero as a point on a temperature scale. A map may use 0 degrees of latitude at the equator, or 0 degrees of longitude at a chosen meridian. In physics, an equation may describe a balance when a total force is zero, or a starting condition when time is set to zero. Zero helps scientists say, begin here. It also helps them say, there is none of this quantity, or this is the reference from which we measure. The meaning depends on the setting. Zero may mean no amount. It may mean a starting point. It may mean balance. It may mark an empty place in a written number. It may be a boundary between positive and negative. Its quietness allows it to serve many roles. Zero also helps us write the very large and the very small. In positional notation, a system of place value that grew from earlier numeral traditions, each position has meaning. A zero can hold a place so that a number keeps its shape. In 1000, the zeros show that the one stands in the thousands place. In 0.001, the zeros help show a very small quantity, 1,000th. A row of zeros can stretch a number outward into great size, or inward into fine smallness. They make it possible to write distances between planets, the width of a cell, the age of a star, the charge of a particle, the scale of a map. A small mark, repeated calmly, lets the mind travel far. One might imagine a quiet room in the evening, a window open to cool night air. On the desk lies a sheet of paper. A graph rests there with its origin at the center. A curve bends across it. Chalk dust settles on a dark board nearby. Outside, the stars seem scattered like points on a vast coordinate plane, each with a place, each held in the silence. Zero sits at the center of the page. It is not loud. It does not announce itself. Yet from it, directions begin. Around it, equations find balance. Near it, calculus studies change. Beyond it, the thought of infinity opens like a long horizon. The story of zero, once a story of empty spaces in clay and small marks in manuscripts, has become a story of motion, measurement, and vastness. It has touched algebra, geometry, science, and the way we imagine number itself. And yet, after all this widening, zero remains familiar. The mind can return from endless lines and starlit coordinates to the ordinary world, where the same small symbol waits quietly on clocks, thermometers, computers, and pages of numbers. A circle of nothing that means something. A quiet center, ready to be used again. Chapter 12. The Quiet Center. A digital clock glows softly in a dim room. Its numbers are simple and familiar, made of small bars of light. An hour turns, a minute changes, and there it is again, zero. It may appear at the beginning of the morning, in 0600, or at the turn of midnight, in 000. It may sit at the end of a number, making 10 from 1, or 100 from 1, with 2 empty places beside it. It is a small sign, rounded and quiet, like a little moon on a page. After such a long journey, zero has become ordinary. It lives in the corners of daily life so naturally that we often pass over it without notice. Yet inside that ordinary mark is a long human story. Stones in a hand, tallies on bone, marks in damp clay, sky watchers under the moon, palm leaf manuscripts, libraries, ledgers, printed books, chalk lines, and now the soft glow of screens. Zero began in part as a way to show an empty place, and it is still doing that. On a calendar, zero helps arrange the days and years into orderly forms. In a phone number or a postal code, it may not mean nothing in the usual counting sense. It is part of an address, part of a pattern, part of a way to find someone or somewhere. A zero in a code can be just as important as any other digit. If it is missing, the message may point to the wrong place. On a thermometer, zero can be a reference point. In the Celsius scale, 0 degrees marks the freezing point of water under ordinary conditions. Snow may gather quietly beside a window, and the thermometer may rest at 0, not saying that there is no temperature, but saying where the measurement stands on that particular scale. In a bank balance, 0 may mean balance, nothing owed, nothing held, a line of stillness between positive and negative amounts. In accounting, it can mark absence, but it can also mark completion. A debt paid down to 0 has a different feeling from an empty shelf or a blank page. The same symbol changes its meaning gently, depending on where it is placed and what question it is answering. This is one of zero's quiet strengths. It can mean absence, it can mean a starting point, it can mean balance, it can mean an empty position inside a larger number. It can mean a neutral amount, the amount that changes nothing when added. Mathematicians call this last role the additive identity. The phrase sounds formal, but the idea is simple. An additive identity is a number that leaves another number unchanged when you add it. 5 plus 0 is still 5. 1,000 plus 0 is still 1,000. 0 joins the sum without disturbing it, like a silent companion walking beside another number. In this way, 0 is not only emptiness, it is also steadiness. A pencil rests beside a page of numbers. Some are large, some are small. Some carry decimal points, some stand in long columns. The zeros among them may seem plain, but each one helps the page make sense. In 105, the 0 holds the tens place open. Without it, the number would become 15, something quite different. In 1005, 2 zeros make a spacious distance between the thousands and the ones. They are not counted as objects, but they shape the number's meaning. This was the ancient problem returning in a modern form: how to write an empty place so that it is not mistaken for nothing at all. The old Babylonian scribe pressing wedge marks into clay would have understood part of this need. The Indian scholar placing a dot or small circle in a line of numerals would have understood more. The merchant closing a ledger at dusk would have felt its usefulness. And the modern student writing 10, 100, or 1,000 continues the same human habit, making room for emptiness so that meaning can remain clear. 0 is also at home in coordinates. On a graph, the origin is the starting point, often marked by 0. It is where directions meet and measurements begin. From that quiet center, one can move left or right, up or down, forward or back. A map, a screen, a design, or a scientific measurement may all depend on some chosen 0 point. It is not always the center of the universe. It is simply the agreed place from which we begin. A point at 0 can be humble and powerful at the same time. It says, start here. In science, 0 helps describe the very large and the very small. Scientific notation, a compact way of writing numbers, uses powers of 10 to keep long strings of digits manageable. 0 helps build those powers. It makes 1,000,000 easy to write. It makes 1,000,000th possible to place carefully on the page. It helps measurements travel from the size of planets to the width of cells, from distances between stars to tiny changes in a laboratory instrument. The same round mark can stand near both vastness and minuteness. And then there are computers, humming quietly in rooms, in pockets, in buildings where rows of servers breathe out a steady warmth. Deep inside their operations, 0 is paired with 1. This pairing is called binary. Binary is a base 2 number system, which means it uses only 2 symbols, 0 and 1. With just these 2 signs, computers can represent data. Data means information that is stored or processed. A letter, a color, a sound, a photograph, a number, a message sent across great distances. In one setting, 0 may mean an off state, while 1 may mean an on state. The real workings of modern machines can be very complex, but the basic idea is gentle enough. Two simple symbols can be arranged in long patterns, and those patterns can carry meaning. A song may be stored through patterns involving zeros and ones. A map may be drawn. A message may cross an ocean. A picture may appear in light. Here again, 0 is not merely nothing. It is part of a language. It helps make a pattern readable. It gives contrast, spacing, and structure. In the quiet logic of computing, the empty sign is deeply full of use. Still, 0 keeps its older meanings too. It can be the empty basket, the open place in a column, the mark that says none, the balance point between gain and loss, the beginning of a line, the circle at the center of a clock. This is why the story of 0 is not the story of a single invention made in a single moment. It is the story of people learning over centuries how to write absence, how to calculate with it, how to trust it, and how to let it become part of thought. It moved through many hands. A shepherd may once have counted stones to match animals in a herd. A scribe shaped damp clay with a reed stylus. A skywatcher wrote careful numbers beneath the stars. Philosophers wondered about emptiness and the void. Indian mathematicians gave 0 a place among numbers. Scholars in Arabic and Persian wrote, translated, taught, and extended methods of calculation. Merchants carried numerals across seas and marketplaces. Bookkeepers tested them in ledgers. Mathematicians placed 0 on lines, in equations, and at the origin of graphs. Engineers, navigators, scientists, teachers, and programmers found new ways for it to be useful. The little sign remained simple. Its meanings grew. Perhaps that is part of its beauty. 0 does not need to be large to be important. It does not need to announce itself. It sits quietly beside other digits, and the whole number changes. It rests at the center of a coordinate plane, and location becomes clear. It appears in a balance, and a debt is settled. It joins 1 in binary, and information begins to move. A symbol for nothing became a way to make room. There is comfort in that. An empty place is not always a lack. Sometimes it is an opening. A pause in music helps the notes around it be heard. A blank margin gives a page its shape. A quiet courtyard gives a library air and light. A 0 in a number gives the other digits their positions. The round shape of 0 can be imagined as a small moon, pale and calm, or a seed, or a shell, or an open doorway. It is closed in form yet open in meaning. It can hold absence without confusion. It can mark a beginning without noise. And so the long path of 0 settles into the present moment. In clocks and calendars, in temperatures and balances, in coordinates and measurements, in phone numbers, postal codes, scientific notation, and computer code, in the simple sum where adding 0 changes nothing, in the deep history where nothing became something people could write, share, and understand. 0 is both a symbol and an idea. Its power comes from that gentle joining. The mark can be written in ink, carved in stone, printed on paper, or lit on a screen. The idea can move through arithmetic, science, philosophy, and ordinary life. It is simple enough for a child to use. It is subtle enough to keep mathematicians thinking. At the end of the story, 0 remains what it has been all along, an empty place that means something. It does not ask to be noticed, yet it helps the world count, measure, locate, balance, and remember. A small circle rests on the page. The page is quiet around it.